Alrighty. Well, I will begin with a word of prayer. So, dear Father, we thank you for this day. Again, I thank you for this class and these students. Just ask that you'd be glorified in what we do this day, and that we just all learn a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so today, I guess first I'll ask any questions about anything in particular.
Which problems are being omitted from the homework?
I said in the announcement. I don't remember offhand.
I just said that 111 through 115 are doubled up, unless somebody saw different, but I didn't say which ones were omitted. Oh,
Maybe I put it in the. It might have been in the was it in the subject or something? I didn't repeat it in the message. Yeah, sorry about that. I do that sometimes. Okay, so yeah. Yes, sir.
I know there's some parts that we have to use a computer. Do we have to show any of our work for that?
Yes.
What are you sort of expecting as far as showing?
I expect you guys to you probably use MATLAB or something like that. Yeah, and so you should print out the file that shows the work.
We should print that.
Yeah. And so yeah, we'll get back to that. But other questions? Okay. So we've talked about the solution. Let me remind you guys. Previously, we solved dx dt equals to ax with eigensolutions, right? Like if we had a minus lambda I times, let's say, u equals to 0, then we talked about how x equals to e to the lambda t times u solves star, right? However, we notice that this doesn't always give us enough solutions, right? Because a matrix A doesn't have to be diagonalizable, right? What did we say about diagonalizable? Also, right? A is diagonalizable if and only if what? There exists an eigenbasis, right? Let's say V1, V2, Vn, where the basis matrix inverse times A times the basis matrix, again, diagonalizes it, right? It gives us, and what was the diagonal form? It was the eigenvalues down the diagonal, right? And so, first of all, if, strictly speaking, if all of the eigenvalues are not real, if one of the eigenvalues is complex, most people would say that the matrix is not diagonalizable in that case. What they really mean is it's not real diagonalizable. It may still be complex diagonalizable. But there are matrices which are not even complex diagonalizable, all right? So the question is then, what do we do about these kinds of matrices? And also, what do those kinds of matrices have to do with the missing solutions to star, right? And so that's what I want to start to talk about today, is the so-called the so-called Jordan form. So today we're going to talk about the Jordan form. All right. And so in order to talk about the Jordan form, I need to define some new kinds of vectors for us, all right? So we can appreciate the form. So let me start with that. Definition. We say V not equals to 0 is a generalized eigenvector with eigenvalue lambda. I missed two words here. Of order p, all right, with eigenvalue lambda, if a minus lambda I to the power p minus 1 acting on v is not equal to 0, yet a minus lambda I to the power p acting on v is equal to 0. This makes v a generalized eigenvector of order p for A, right? This is all with respect to the matrix A, all right? So like, kind of silly comment, what is it, what is order 1, what's this make order 1? It gives us back a plain old eigenvector, right? Just a garden variety eigenvector, right? Because what is 1 minus 1? 1 minus 1 is 0, right? Any matrix to the 0 we define to be the identity. So this condition collapses to just saying, you know, v is a non-zero vector such that a minus lambda I multiplying v gives me 0, right? That makes it an eigenvector. All right. So that's first definition. Second definition is that if we have v1, v2, vk, all not equal to 0, such that the first one times a minus lambda I is equal to 0. In other words, the first vector is a plain old eigenvector, and a minus lambda I acting on vj is equal to vj minus 1. Let me hold on a second, hold on. Other way around. My bad. Vj plus 1 is equal to Vj for j equals to 1 to all the way up to k minus 1, I think. Yeah. Then v1, v2, vk is a k-chain of generalized eigenvectors with eigenvalue lambda. Let me unravel what this means for us, because it's going to be important both to understanding what the Jordan form is, but also to understanding how to solve that equation at the top star. It's part of the same animal. So, all right, so let me write these out over here. So suppose we have a k-chain. All right, so that means to start with, we have a minus lambda I, v1 is equal to 0. What happens when we take a minus lambda I, v2? What do we get? I'll just do a few. So v2 maps to v1 like this, right? v3 goes to v2, v4 goes to v3, all right? That's what the chain condition right here says. All right, so what happens then with this second equation here if I multiply by a minus lambda I squared, again, right? What is a minus lambda I v1 though? It's 0, right, by the assumption. right? So therefore V2 is generalized eigenvector of order 2. All right. Let's do this for V. What happens when we multiply V3 by A minus lambda I? Well, we get V1, right? But what happens when we multiply it again? A minus lambda I cubed acting on V3. That puts A minus lambda I in V1, which gives us 0, right? So I won't write that down, I'll just write this down. So what does this mean? V3, generalized eigenvector of order 3. Starting to notice a pattern. What do you think is going to happen next? So we do, that goes to V2, right? Yeah. And A minus lambda I cubed on V4 gives us V1. And then finally, A minus lambda I to the 4th on V4 gives us 0. So therefore, V4 is generalized eigenvector of order 4. All right. So there's a theorem, right? Vj is generalized eigenvector of order j for the k-chain as denoted back there, all right? So when we have this situation, this is part of what we mean by a Jordan basis. A Jordan basis is going to be when you have a basis which is formed by a union of k-chains for a given matrix, all right? And if we have a basis which is a union of k-chains for a given matrix, when we calculate the matrix, the form of the matrix with respect to the similarity transformation, like beta inverse A beta, it's going to put the matrix into what's called Jordan form, which is not diagonal necessarily, but it's the next best thing. So let me show you some explicit examples of Jordan forms, yeah? So I guess example 1 here, if we had A equals to 3, 1, 0, 3, this matrix here, we have A minus 3i times, E1 is equal to 0, and we have A minus 3i times E2 is equal to E1. What is A minus 3i, by the way, for this matrix? It's just this. So once you write that down, it becomes kind of stupid what I'm saying about E1 and E2, right? Of course, when you multiply by E1, you get 0 because the first column of that matrix is 0. Yeah? And of course, the second, E2 times the matrix gives us E1 because the second column is E1. So we know any matrix times EJ gives us the jth column, right? We should know this. Of course, you could also do the matrix multiplication, but, I'll be honest, I don't. I think in these terms. Okay, so, great. So this makes E1, E2 a 2-chain with eigenvalue 3 for A. So basically, here's the deal. If the standard basis is a Jordan basis and things are in their proper order, the matrix you're looking at is what's called the Jordan form. This A I gave you is nothing more than, by definition, the Jordan block. So this is J 2 of 3. Here's a definition. The Jordan 2 by 2 block for eigenvalue lambda is exactly lambda 1, 0, lambda. So this is a notation. The 2 by 2 Jordan block. With, eigenvalue lambda. All right, what do you guys think the 3 by 3 Jordan block looks like? I'll get you started. We're going to put lambdas down the diagonal. We're going to put zeros below the diagonal. So the Jordan matrix is always like upper triangular, right? Well, the Jordan block is upper triangular, I should say. Is the Jordan form upper triangular? Oh, yeah, it is. Okay, so then what we do is we just put ones here and here. All right, that's by definition the 3 by 3 Jordan block. All right. So let's make it a little bit more specific. Example 2. If I have A equals to 4, 4, 4, 1, and 1 on the super diagonal here, right? This is the 3 by 3 Jordan block with eigenvalue 4. What does this make A minus 4i? It makes it equal to that matrix, right? That's a special matrix, by the way. It's a really special matrix. That red one I just wrote. It has a neat property. Actually, this has a name as well. I call this thing N3. By the way, back here, A minus 3i, my label for this is N2. All right. Anyway, I think you probably can see, without much effort, that A minus 4i times E1 is 0. A minus 4i times E2 is E1. A minus 4i times E3 is E2. That makes E1, E2, E3 a 3-chain for A with eigenvalue 4. Now this N2 and N3, this is the so-called nilpotent matrix. I should say it's the nilpotent matrix because it's the one of reference. There are many other nilpotent matrices, but these ones are especially interesting to me. A matrix is said to be nilpotent. Just a little language. B is nilpotent of order P if b to the p minus 1 is not equal to 0, yet b to the power p is equal to 0. So, definition, n sub k is the k by k matrix with ones on the superdiagonal and zeros elsewhere. So like I already wrote down n2, I'll write it again. n3, n4, I think that's enough. You get the idea? Right? Check it out. n2 squared is, there's a really neat pattern to see guys here. So n2 squared is 0. n3 squared, what happens there, as you square these matrices, it moves the superdiagonal like up towards the corner. That's the effect of the matrix multiplication. It's like, it pushes this band of ones up to the corner. So in this case, when you work it out, you get this. On the other hand, n to the 4th squared gives you this. So it's like it moves the band of ones up to the corner. That's the effect of multiplying it by itself. So like n cubed, what happens when you multiply again? n3 cubed is 0, right? Because you basically just end up moving the 1 off the edge. And, well, n4 to the 3rd power I don't know why I'm writing so many zeros, but there it is. n3 to the 4th power is the one that's got the 1 in the upper corner and nothing else is non-zero. And then finally n to the 4th is equal to 0. All right. So in retrospect, we could use this nilpotent matrix to sort of explain the form of the Jordan block. If you go back and you look at my Jordan blocks, right, we can say a little bit more, right? What would the k by k Jordan block be? What we would do is lambda times the identity matrix plus n sub k. And that's the k by k identity matrix. Right. Which I can write out, I guess, if it would help you. But I don't know if it's really as good. I mean, it's okay, but it's ugly. This is the k by k Jordan block. All right. So, to put a matrix in Jordan form, all right, what does that mean? Guess I need some more space. All right, you guys have this all memorized now, so we can erase it. All right. I'll present it kind of as a theorem. If beta is formed by union of k-chains, let's say k-chains with eigenvalue lambda sub I respective, all right, where let's say k1 plus k2 plus da 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 plus k sub, let's suppose it takes r chains is equal to n, right? Then I'll put an I here. beta inverse A beta is equal to J K1 of lambda 1 direct sum J K2 of lambda 2 direct sum direct sum J K R of lambda. In other words, this is a block diagonal matrix where the blocks are Jordan blocks, as I've defined earlier today, all right? And so the theorem, well, that's basically, that's a roadmap of how you'd find the Jordan form if your matrix wasn't already in Jordan form, all right? If the matrix not already in Jordan form, if you can find a Jordan basis, the similarity transformation to that basis gives you the Jordan form. Now, the interesting perhaps, well, no, it's not perhaps, it's definitely interesting. The interesting theorem is that, in fact, for A, as long as A has all real eigenvalues, right, if A has a set of real eigenvalues, then the Jordan form exists. In other words, a Jordan basis exists for any matrix which has all real eigenvalues. Yep.
The n there that's the sum of the case, is that the A is an n by n matrix?
Yes. Yeah. For A in R n by n. Thank you. Now, there's nothing especially special about the real numbers here. You could also talk about complex Jordan form, right? There you would have the luxury of knowing for sure that the Jordan basis exists because complex eigenvalues always exist. If we're working over the complex numbers, any nth order polynomial automatically has n solutions possibly repeated. So this trouble of there may or may not be eigenvalues for your real matrix goes away if we take a complex perspective, all right? And we'll circle back to that another day. That idea, as it contacts with the real matrix, brings us to something else, which is called the real Jordan form. The real Jordan form uses little 2x2 blocks of matrices, which correspond to like our rotation matrices earlier times reflections, as it turns out, right? That's the other thing that can happen, of course, because not every, like, as you look at the equation star, you're thinking about A as an arbitrary n by n matrix. It doesn't have to be the case that A has n real eigenvalues. So this machine I'm describing to you today may not apply, right? If it's the case that one of the eigenvalues is complex, then we need to consult the real Jordan form, all right? Okay, so let's talk about star, though. We got all these equations in front of us. We should use them. All right, so like, let me give you a specific example. Maybe I should give you the general formula first. Let me think. I think I'll put it there. Yeah. So, something I need to introduce for you guys is the matrix exponential. In other words, how do you take the exponential of a matrix? Well, the answer is with a series. So here it goes. E to the TA is equal to I plus TA plus 1/2 t squared a squared plus dot 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 dot. So generically speaking, it's the sum, let's say n equals 0 to infinity, of t to the power n divided by n factorial times a to the power n. This is the matrix exponential. We can prove that the matrix exponential converges for any matrix A. All right, the matrix exponential converges for any matrix as it happens. And better yet, if you study differential equations, what you find out is that the matrix exponential contains in it all of the solutions you need for your problem. It's actually what's called a solution matrix to the equation star, meaning that every column is separately a solution to dx dt equals to ax. So like, in a nutshell, here it is, theorem dx dt equals to ax, right, has solution x of t is equal to x sub naught e to the ta with x of 0 equals to x sub naught. In other words, that's the solution to the arbitrary initial value problem for dx dt equals to ax, where A is an n by n matrix. So this is the solution to an arbitrary n by n homogeneous system of first order differential equations. All at once with this one foul swooping thing, the matrix exponential. But the cost, right? First of all, I don't know how to multiply. That's a bad thing. Can I put the x naught here? Search your heart. Find this to be nonsense, right? I'm taking a vector times a matrix. Is this good? This should have not been good to you since about week 2 in this course, right? You should have a sense of righteous indignation that I wrote that. You should be like, no, I want a refund. The professor doesn't know what he's doing. There we go, that's better. Now we've got an n by n matrix times an n by 1, which gives us an n by 1, which is what we'd like, right? Anyway, that's lovely, but how do you actually calculate e to the at, right? It's an infinite series of matrices. How do you actually calculate it? It's kind of scary, isn't it? So let me show you an example where we can calculate it. What if we look at e to the t times, I don't know, let's do n sub 2. So we've got I plus t n sub 2 plus t squared over 2, n sub 2 squared, plus dot 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 dot. But what did we just learn about n sub 2? It squares to 0. Yes. So whoop, whoop. This is just I plus t n sub 2, which if I write it out is 1, 0, t, 1. So what I'm claiming is simply this. If I look at the differential equation x1, x2 prime is equal to like 0, 1, 0, 0 times x1, x2, it has solution x of t equal to 1, t, 0, 1 times like my initial vector. Let me just call it C1, C2 for lack of imagination. Yeah. So your general solution is like C1 times 1, 0 plus C2 times T1. That would be like the general solution to this differential equation via the matrix exponential. Well, you can easily check that these two like solve this, right? Like if you go back and unravel this thing, it's a rather silly system. It's x1 prime is equal to x2, and x2 prime is equal to 0, right? So if you look at the solutions, I've got like 1, 0, and t1. So in both cases, x2 is constant, right? And the derivative of the first one is either, well, anyway, if you look at it, both of these vectors solve this system. Think through it. Okay, anyway, let me go on here. I'm taking a slightly different approach than I did in my differential equations class. So if you're also in there, maybe we'll see something a little bit different here. In differential equations, I usually teach what I call the magic formula, and maybe I'll do that next class. I do think that's worthwhile. Maybe if I have time today, I'll do it. Probably not. Let's see here. Where was I? The marker that works. What happens if we take e to the how about e to the t n k? What happens there? Well, let's do just 3. So we've got I plus t n 3 t squared over 2, n3 squared, plus 0. Lots and lots of zeros, right? So that works out to 1, 0, 0. T's on the super diagonal. And this n3 squared gives us a t squared over 2 up here. All right. Example 5, what happens if we look at e to the tn4? We have I plus tn4 plus t squared over 2, n4 squared, plus t cubed over 3 factorial, which is 6, right? Maybe I'll write it as 3 factorial just for the sake of the pattern, though. N4 cubed. And then plus stuff that's 0. Zeros. All right, so what's that work out to? We've got 1s down the diagonal. We've got t's on the super diagonal from the n4 term. We've got t squared over 2, or if you like, t squared over 2 factorial. I'll just write t squared over 2 there. And then we've got t cubed over 3 factorial in the upper spot there, and zeros below the diagonal. My point to you is simply this. If we have a matrix which is nilpotent, we can calculate the matrix exponential of it pretty easily, because this like infinite series just truncates the first couple terms, because we're given that the matrix past that point is 0, right? Now, if all matrices were like this, then matrix exponentials would be like way less intimidating, because you know what you got to do. You just got to keep multiplying until it gets to 0. But not all matrices are like this, right? Certainly not, you know. All right. So, comment, well, really another theorem. If A times, well, let me step away from A and B. Let me say M times N is equal to N times M. Then e to the M plus N is equal to e to the M times e to the N. In other words, the matrix exponential satisfies the usual laws of exponents for matrices which commute. If you have commuting matrices, then you have this lovely simple law of exponents. So notice, for example, that if we take lambda times the identity, the k by k identity matrix, times n sub k, well, that's equal to n sub k times lambda times the identity matrix, right? In other words, the identity matrix and the nilpotent k by k matrix, these commute. They commute, which means that I'm well within my rights if I look at e to the t times, lambda k times I k plus nk, right? That is equal to e to the t lambda k I k times e to the t n k. And the thing is, we know how to calculate e to the t n k. I just showed you in the previous series of examples. That's explicitly calculable. And it turns out that when we study this carefully, this simplifies simply to e to the lambda k t times e to the t n k. This is scalar. Right? I'm using yet another theorem which says that if we have e to the t times a diagonal matrix, let's say d1 dn, then that's equal to the diagonal matrix of, I don't need the t here necessarily. The diagonal matrix is equal to the diagonal matrix of e to the d1, e to the d2, e to the dn. Maybe I'll work that out for you guys next time. Let me just state it as a hey, look at that. But what that implies, though, is that if I have the matrix exponential of lambda times the identity, that simplifies simply to this scalar exponential. All right? Okay, so you're like, well, this is great, but what is this? How does this help? You know, and that would be a good question. Well, look at this. So what we've just shown is that that's the formula for e to the t times the k by k Jordan block, right? So we have a formula for calculating the matrix exponential of a Jordan block. This is very nice. There's more, though. Because the matrix exponential plays nice with similarity transformation. So, definition, B is similar to A if there exists invertible P such that B is equal to P inverse AP. All right? This is what we mean by similar matrices. We've talked about this a little bit before, I think. But it turns out that if you have P inverse e to the ta times P, we can calculate that this is in fact equal to e to the t times P inverse AP. So, thus, we can write e to the ta as equal to p e to the t times P inverse AP times P inverse. But the thing is, if we're strategic about this, if we choose P to be the matrix corresponding to a Jordan basis, right, then we can make, if we make P equal to the basis matrix for beta a Jordan basis, then P inverse AP is equal to like J1 direct sum J2 direct sum JR, where these are all Jordan blocks. Well, we already know how to calculate the matrix exponential of a Jordan block, right? What about the direct sum of Jordan blocks? How's that go? Well, good news. If you have the matrix exponential of, say, A1 direct sum A2 direct sum AR, this is equal to, in fact, e to the A1 direct sum e to the A2 direct sum e to the AR. This is how the block multiplication works out. Because we're talking about a block diagonal matrix, the power of a block diagonal matrix is simply the block diagonal matrix of the powers. And then the definition gives you this immediately. So like, just to be more explicit, if I was to calculate e to the 3103 2102, I could do e to the 3103 direct sum e to the 2102 like this. But this, by my other calculation, is e to the 3 times, let me stick some t, put a t here to make it match the other thing. We just calculated e to the t and 3 is, 1t01, direct sum, that's a t, e to the 2t, 1t01, which explicitly is, well, anyway, this is, let me not write it out, this is a 4 by 4 matrix. All right, so anyway, I have tried to, today, get us started on what is the Jordan form, how do we understand it. I have yet to explain how to calculate it, right? I've showed you examples. I didn't at all really explain how do you find the Jordan form for a matrix, but that is mostly what your take-home test 3 is about. So I have some explicit, I only have 20 of these. I think there's more than 20 to use, so my apologies. But this is group work, so like, how big is the group? I don't know. As big as it gets, I guess. So like, you could work in groups of 3, you could work in groups of 4, or 5, or 10, 30. I think there's an upper bound on like about 32. I think that's all the students we got in here, right? Something like that. So, well, wait a minute. Did I actually have enough? So, oh no. Yeah, I'll get you one here in a second. I'm sorry, man.